Thank you so much for the introduction, Altem. My name is Yudai Tanaka, and I'm going to talk about my work with Akifumi Takahashi and Pedro Lopes at the University of Chicago. Let's start by observing two identical haptic interactions side by side in virtual reality. As the user pushes this box, a haptic device contracts the muscles to render its resistance. Here on the left, something seems wrong with the user's experience, so they got out of it. They seem very distracted. While on the right, this same user is fully engaged and enjoy the experience with no distraction. But how can these same interaction can result in such a different user experiences? The answer to this and my motivation comes down to these two small fabric pieces. Turned out these are electrodes. They apply tiny electrical currents to the user's skin, reaching and stimulating the muscles and actuating their body, which is called electrical muscle stimulation, EMS. Over the last decade, this technique has gained popularity in providing force feedback in interactive experiences, such as posing the finger, adding haptics in VR, or even augmenting our ability. With this small form factor, EMS became a popular actuation technique, with more than 300 papers published over the last 10 years in HCI. However, while EMS is so popular, these works don't highlight the key issues, which I know from my heart because I've been practicing this technology for over years, which is first, electrical currents have to travel through the user's skin before they reach the muscles to move it. While the movement is what we wanted, when they cross the skin, they stimulate and they create a very uncomfortable tingling sensation in their skin. This is totally unwanted and not the goal of force feedback. Moreover, you have to adhere these electrodes directly to the skin, and these sticky electrodes are gel-based and hard to detach and need replacement every after use time of usage. So our goal here is to just create force, and we don't want the side effects of tingling electrodes. So here's my proposal. Can we just create electrical currents inside the body without attaching any electrodes that interfere with the skin? What if we don't use electrical stimulator at all, but instead use a magnetic stimulator? This is a magnetic stimulator, medical grade, and magnetic coil. Let's use this one. So now the user took off their electrodes and hovered their arm over the magnetic coil. The magnetic field from the coil intersects with the body, subsequently creates electrical currents reaching to the muscles, but less of them have to go through the skin, resulting in a similar involuntary actuation, but this time with much less skin interference. We call this magnetic muscle stimulation, MMS. So my proposal is that let's use magnetic stimulation for interactive force feedback, because there are a number of key benefits that we discovered through our user studies. First and foremost, we evaluated how magnetic stimulation could reduce the skin tingling of EMS and make it more comfortable, as the current distribution in the magnetic stimulation is very different from that of EMS. So we applied EMS and magnetic stimulation to the user's arm and asked how much uncomfortable tingling they felt. As a result, the tingling from magnetic stimulation was significantly smaller than that of EMS in all three intensities. This means if you're using EMS and if you care about the comfort of the experience, here you go. This is the way. You can make the experience twice more comfortable by simply switching to magnetic stimulation without any other modification, no code change. As a downstream effect of this reduced tingling, we proved realism of the force feedback. So we immersed the participants in the two VR experiences. One, pushing the box and feel the resistance in their arm. Two, pulling up this lever and feel its weight. What we found is every time when the user pushed this box or pulled up that lever, they felt like feedback was more like an actual force in magnetic stimulation. This means if you want to make the force feedback in VR more realistic using EMS, you can simply switch to magnetic stimulation and you can achieve it, right? So with this improved realism, what can we do? I can destroy my advisor's work from Kai 17 using EMS for haptic realism. This same box feels much nicer, and she doesn't even need to wear the electrodes or take off her clothes to attach the electrodes. Not just realism, we even thought the less tingling could make it even easier for the user to feel the movement and pulse in magnetic stimulation. So we tracked the user's hand and measured how accurately they could recreate the hand pose after the stimulation. Turned out, the participants could more accurately recognize and remember the pose created by magnetic stimulation, shown in this smaller error. Again, if you're using EMS and want to clearly communicate movement and pose, this is a way that could give it away right now. With this clear pose perception, I can also destroy another work from my advisor. The stimulation to muscle for input and output. So here the coil is inside a couch, and then as the user activates, the magnetic stimulation outputs the playback position of this video to the wrist pose that can be clearly recognized in eyes free. They can also control this video scrubber by moving their wrist. And cherry on top, all of these things can happen up to 5 centimeters with more than 1 Newton force that is enough to move your fingers. With this distance, we can, for instance, attach a coil to the chair to provide the sense of inertia in a driving simulator by stimulating the user's back. All right, we just looked through the key benefits of magnetic stimulation: comfort, realism, clarity, and non-contact. But I have to acknowledge, magnetic stimulation is not the solution for everything. One thing is that it's louder than EMS. By now, I think maybe you may have recognized magnetic stimulation generates this sound. We need to be selective to the sound context of interaction, but more critically, the coil is much larger than the electrodes. So we want to be creative about how to place or even hide the coil and design the interactions. One option is to simply embed the coil, as you saw on the chair, in the couch, or we can take this further. We can even envision embedding this coil behind the handrail in a public space like a train. So here, as the train, user is in the train, suddenly accelerates, the stimulation actuates the back of the hand to safely grabbing the handle, preventing them from falling. Another option is to simply wear the coil. So even though it's heavy and large, if your experience is short and you don't move too much, you can just wear it and feel the force in BR, for instance. While in all these examples so far, the coil was fixed in one point, we can also move the coil with the robotic actuators so the user don't voluntarily align their body to the coil. So here they feel the impulse through the shoulder actuation. So today, I pointed out that we can remove these electrodes from EMS and consider magnetic stimulation as an alternative because there are so many benefits to be gained. But more importantly, I am so excited, as you could have tell, about this work because in my PhD, I'm always thinking about haptic devices that intercept the nervous systems instead of covering up the skin, for instance. So for instance, in my Kai paper last year, I proposed intercepting the user's neck muscles to actuate the head, rather than using an exoskeleton attached to the head to mechanically move the head. Magnetic stimulation also intercepts the nerves, but it even opens up a potential to enhance the quality of any haptics in this regime. Thank you so much, and I'll take questions.
Hi, Purnendu from University of Colorado Boulder. So great work. I have two questions. So first is that you showed a robotic platform where the like the coil can move around user's head. But so as I understand, if you want to have multiple haptics, haptics at multiple body locations at the same time, you would either need multiple coils or a robotic system. What could be a wearable analog of this? Why I'm asking this, that could it be a head-worn thing where it stimulates your brain? What do you think about this?
Okay, so as I'm working on this regime, I kind of found like kind of trade-off in this kind of field of intercepting nervous system. So hypothetically, I think we can create the haptics by stimulating the brain, but all the body parts like motor and sensory information are cramming into like this like less than 10 centimeters region. So current maturity of the non-invasive stimulation, I think it will be quite difficult and challenging to, for instance, specifically moving your wrist only or something like that. So I decided to, instead of stimulating the brain, I decided to locating a coil in the peripheral position. That is the rationale for this work.
Okay, cool. Thank you.
Thank you.
Hi, Yudai. I'm Yuzia from Stanford University. Thanks for your great talk. My question is specifically around your study one when comparing EMS versus MMS. I'm curious how much trials did you actually stimulate the participant, and also I'm curious if over time you see like the EMS condition, the user actually adapt to the tingling sensations, and if it's actually like you don't feel that much tingling over time.
Exactly. You know it, right? Okay, so yes, there is adaptation, and we did have 2 repetitions for both study one, the comparing the tingling, and also the BR realism ones. And these order of the tasks and then the different trials are all taken into account for this. For the statistical test, which you can check in the paper, but we didn't see the interactions or effect or the effect of the order. So even they both adapt. So EMS might get better, magnetic stimulation could also get better.
Okay, thank you.
This is Yu Jiang from Zhao University. I have a really general question about why are you specifically comparing EMS to MMS? I know EMS has always been your own research direction, but then there are also a lot of other haptic simulation like pneumatic and vibro-tactile. So are there any similarities? So why are you specifically comparing these two?
I see. Thank you so much. I take this as kind of like my personal mission, and then also in HCI community, comparing to robotic device and pneumatic, EMS has become the most popular way. I did some meta-analysis for that. So I thought it would be very nice to kind of like chime in, and then there are so many people working in EMS, and kind of like deliver the message of we can start thinking about the alternative. We can also offline talk about like why I didn't include, for instance, like robotic exoskeletons or pneumatic devices. I have some rationales for that as well, so we can talk later. Thank you.